the next lesson, which is the line of best fit using the mean point. So line of best fit probably makes sense when you're doing a scatter graph. You've probably done them in science class for ages. But something that is new to you is the fact that when you draw a scatter graph, before you draw the line of best fit, you need to first plot the mean point. And the mean point is a special coordinate, and the x-coordinate is the mean of all the x values, and the y-coordinate is the mean of all the y values. And so you then need to plot that extra coordinate, and your line of best fit, you need to make sure that the line of best fit goes through that mean point. That's exactly what the examiners are looking for. So let's go to the beginning of this lesson. Okay, so a scatter graph shows whether there is a something between two something. So a scatter graph shows whether there is a relationship, you could say. You could also say correlation, so feel free to also use that. We'll be using more so the word correlation. But in general, it's kind of, is there a relationship between two variables? So a scatter graph shows whether there is a relationship or not between two variables, the x and the y. So something that's important, you have, on your scatter graphs, you have an independent variable and you have a dependent variable. So by definition, the independent variable appears always on the x-axis. So in your scatter graph like this, you've always got the independent one down here, and the dependent one is on the y-axis. So that's how scatter graphs are kind of defined. So the independent variable always appears on the x-axis, and the dependent variable always appears on the y-axis. The independent variable causes the dependent variable to change. So, for example, an example would be if time would be an independent variable, if temperature was a dependent variable, like in a science experiment, for example. Perhaps you're seeing, like, what is the change in temperature due to the change in time? So the temperature would be the dependent variable, therefore on the y-axis, and time is the independent variable in this case. So it's on the x-axis. The time causes the temperature to change. It's not the other way around. The temperature does not cause the time to change, of course. So that's kind of how you kind of define dependent and independent variables. So more specifically, a nice word, correlation, with regards to the relationship between two variables. You might have heard about correlation in some earlier years, like Year 7 statistics. Correlation refers to whether or not there is a relationship between the two variables. So if, for example, you had something like temperature and, let's see, temperature does affect a lot of things, so that's not a good example. What if you had something like, for example, your height as the independent variable and someone tried to say your IQ as the dependent variable? So of course there'd be no correlation there because there's no relationship between height of a person and their IQ. Where correlation is when more tests of whether or not there is a relationship. Whereas something, if you did a science experiment and it was talking about the change in temperature with time as you heat the fluid, so that, of course, there is a correlation between those two variables because it makes sense. So correlation refers to whether or not there is a relationship between the two variables. It can be something starting with P or something starting with N. So back to Year 7, can you remember? It can be positive. You can have a positive correlation. If it's a positive correlation, the scatter graph's kind of generally going upwards like that. Or it could be a negative correlation. A negative correlation, the general trend is going downwards from left to right, whereas positive, it's going upwards from left to right, or non-existent. If it's non-existent, then it might just be a random scattering of coordinates, and there's no real upward or downward trend as you go from left to right. So same thing, that was just really a review of correlation from Year 7 statistics. Types of correlation. So as we've just been going on about, you can get positive correlation and negative correlation. So if it's a positive correlation, as the something increases, for in this example, we've got temperature and number of ice creams sold. So as the temperature increases, like the independent variable, you've probably noticed as the temperature increases, it causes the number of ice creams sold to also increase. That's what happens when we have a positive correlation. As the independent variable increases, it leads to the dependent variable also increasing. Whereas we have negative correlation as the number of weeks in the top 40 for a song and the number of singles sold. So notice going from left to right, the number of weeks in the top 40 increases. So as the independent variable increases, the number of singles sold decreases for a negative correlation, as opposed to above, where as one increases, it causes the other to increase as well. With negative correlation, as one increases, the other one will decrease as you go from left to right on the graph. No correlation, it's just, in this last example, it's just a random scattering of coordinates. A random scattering of coordinates. There is no upward or downward trend. No positive or negative trend as you go from left to right. So a classic example of that one, as you can see, was house number and IQ. So whether or not you live at number 50 Mill Street or 70 Mill Street doesn't affect your IQ. That just makes no sense whatsoever. So that's an example of something that would come up with no correlation. Just a few more pictures of a few extra examples here. So we've got positive correlation here on the left, and then we have high positive correlation. Even better description of that one, I'd call that one a pretty strong positive correlation. A strong positive correlation. You can say high, but strong is better. So feel free to change that to strong positive correlation. Whereas this one here, it is a positive correlation. I'd call it, more specifically, a moderate positive correlation. Some might say moderate to weak. But comparing the two, you'd say the one on the right is more strong than the one on the left, of course, because the points are closer together on the one on the right. It's a more clear upward trend. Those have got the negative correlation here. Same thing, rather than say high negative, I'd say strong negative. They're technical things now, of course. And same in IB. Strong negative correlation. There's one on the left, moderate, some say moderate to weak. Moderate, okay for now. Moderate negative correlation, just showing you that you can get different degrees of strength. The stronger the correlation, the closer together the points are, showing a more clear trend. So as we said, you can use the word something, something, or something to describe the kind of correlation you find. So the type of correlation, you would say positive. Do that in green, in green. So that's just a summary of what we'll be learning. Positive, negative, or none. Or none, to describe the type of correlation. If we're talking about the strength of the correlation, then you could say weak, moderate, strong, that kind of thing. But in terms of the type of correlation, positive, negative, or none. Something to take into account. These ones, they seem to be clearly like linear trends. But it's possible you might not have a linear trend. You might have kind of a more of a curve, like more of a quadratic style trend. Here's a linear trend, here's a curvy trend on the right. So just be aware of that. It's possible to have different types of trends. So is the trend linear or not? We determine whether or not the points follow a linear trend, or in other words, approximately form a straight line. So these points are roughly linear. Down below, these points do not follow a linear trend. So you could say could be a quadratic or logarithmic trend. That's what is logarithmic trend. Because logarithmic graphs kind of follow this kind of shape, and to some extent, some parts of the graphs do as well. So just the main thing is that you're just pointing out it's non-linear. It's not a linear trend on the one on the right. Whereas the one on the left is a linear trend. They're the main things we want you to be able to see. Because the one on the left is more like a straight line, whereas the points on the one on the right tend to form a bit more of a curve than a straight line. Something to be wary of as well is outliers. What are outliers and how should they be treated in the project? Don't worry about that question. What are outliers? I should click that because we're going to do a project. Okay, so what are outliers? So in your own words, feel free to write it. You don't have to write what I say. So here's an example of an outlier here. Here's an example of not an outlier. That one's not an outlier right there. So you could say an outlier is an extreme point which clearly does not fit the trend. Does not fit in with the general trend. You might have your own worded way of describing it. That will do for now. It's kind of like some people call it freak value, that kind of thing. So just something that clearly doesn't follow the trend. As opposed to this one here is not an outlier because it's still kind of within the trend. Whereas the one that I've shaded in green, that's more clearly an outlier. So normally they're pretty obvious if they're an outlier or not. Let's go on to the next page. Again, is the correlation strong, moderate, or weak? Just showing you a few more examples of that in case you didn't get that. So we've got strong. So these ones are strong, positive. Strong positive. I like to do that in green, don't I? Strong positive, moderate positive, weak positive. So notice as you go from strong to positive to weak, the coordinates become more scattered. But it's still weak positive, the one on the right. It's not to the point where it would be no correlation because there's still some sign of an upward trend as you go from left to right. Same with the ones below, strong negative, almost forms a straight line. Moderate negative, a bit more scattering, weak negative, a lot of scattering. Okay, so example, which graph above shows positive correlation down below? So you probably can't see them all. So which graph below shows positive correlation? See which one, have a guess. What do you think it is? Yes, I agree with you. Positive correlation would be graph A. Just say A. Which one has the strongest correlation, whether it's positive or negative, doesn't matter. Strongest correlation, what do you think? I wonder if you thought the same as me. B, maybe? Okay, it's pretty strong. Yep, pretty less scattering going on there. A is pretty strong as well. B maybe, fair enough. Let's say that it's B. Which graph do you think shows the results in a math test and the height of the candidates? So do you think if you are taller, you will perform better in a math test? Again, this is pretty subjective, so it's pretty hard to tell. If you want, feel free, because we've got to pick a graph for each of these questions. You might want to answer D first and then decide between C and D which are the best answers. So D is the age of computers and their selling price. So we would expect the older a computer, the lower the selling price, because the components are a bit more worn down and the electronics are a bit sketchy after they've been used for so long. So, and certain things could be out of date. So age of computers and the selling price, we would expect a negative correlation. The higher the age of the computer, the lower their selling price. So we expect and that should have a decent correlation. So that should be a decent negative correlation. Whereas the one above should be far less of a correlation. So if we were to do process of elimination here, which one's got the more decent negative correlation? I would say D. So the results in a math test and the height of the candidates. So the results in a math test going higher, the height of the candidates becoming lower. That's pretty weird. But let's go with C anyway. We'll just say C as it has the weakest correlation. No correlation would make more sense. Not weakness, weakest correlation. So no correlation would make a lot more sense. But because we're forced to pick a graph, we'll go with the one that has the weakest correlation. For that one. Okay, let's move on. Little note on interpolation and extrapolation. So if you're asked to plot a line of best fit, so you can read all the information on here, it basically teaches it to you anyway. So when you draw a line of best fit, so if you're asked to use your line of best fit to estimate what is, for example, the height, if you go out to here, and what is the weight up here. So imagine your points, notice that all your points are kind of within here. So if you try to do an extrapolation, if you try to kind of use your line to estimate something that would be kind of out here, that's called an extrapolation. because you're trying to do a calculation outside of the range of data that you've collected. The range of data that you've collected is kind of within these two green lines. So within these two lines is the range of data collected. So if you were asked to come up with a point that was, let's say the height was in here, and you had to find the weight, and you did it within, and the height was in between these two heights here, then that's fine. That's called an interpolation. That's considered reliable because you're trying to make an estimate within the range of data that was collected in your experiments or in your survey. Whereas an extrapolation is when you're trying to do something that's outside of the range of data, like if you knew this height and try to predict that weight. Because we don't know, we only know the data in between these 2 points. Perhaps for all we know, the trend kind of goes like this. So, but we only know that the trend within the range of data we have is kind of linear going from here to here. It's a bit linear. For all we know outside, it might do that. So, for all we know outside, it might start to do this outside the range of data. That's why an extrapolation is considered unreliable, and an interpolation is considered much more reliable. Interpolation is when you're doing an estimate within the range of data that you've collected. Okay, so if you kind of pause and just read through that, then that's kind of going to explain that to you as well. Here's an example. So as you can see, age and distance. So the range of data is from here to here. So within there, if you try to put in an age in between those two values of whatever it was, 10 and 20, that would be an interpolation. So the little one where we've subject 14, that would be an interpolation. So 14, the use of 14 to calculate roughly what the distance would be. So if you went 14, go up to your line of best fit, go across, you get about 26. That's what we would call an interpolation. And that's quite reliable because it's within the range of data that you've collected. Whereas plugging in the age of 30 to get a distance of 78, that would be an extrapolation, which is less reliable because your estimate is outside of the range of data that you've collected. As we said, the trend here is kind of reasonably linear, but for all we know, it drops off, or it goes up instead. We don't know what the trend is outside of the range of data that we've collected. So that's two new words here, interpolation and extrapolation. So note, when asked to draw a line of best fit on a scatter plot, what must you first always calculate and plot? So, as we said before, the mean point. You might not have had to do that in past years. The mean point is a coordinate where you've got the mean of x calculated and the mean of y, and that forms your coordinates. So that, this one's the mean of y, and the other one is the mean of x. Fabulous. How do you then correctly draw your line of best fit? So you must make sure the line of best fit goes through the mean point. Of course you draw it like, you try to fit the general trend as well before, but you must make sure the line of best fit goes through your mean point. So the line of best fit goes through the mean point. So you would have plotted your scatter graph, and then you would have calculated all the x values, or the mean of the x and the mean of the y, and then you'll plot that as an extra coordinate, and then when you draw your line of best fit, you just make sure that the line of best fit cuts through that particular coordinate. Probably best to see it in action. Here's an example. We're going to have to do some graphing. So on a hot day, 6 cars were left in the sun in a car park. That's reminding me that it's warm in the room. The length of time each car was left in the sun was recorded, as well as the temperatures inside the car at the end of that period. So we've got time is your x and temperature is your y. A, B, C, D, E, F stands for the car. So in a way, try to think it's not important. A lot of people think you have to plot that. And that's happened in a few exams. People, for some examiners, for some reason, have put this extra row on top, just saying like, person 1, person 2, person 3, person 4. And students have mistakenly thought that was part of the coordinate. But the x values are the time and the y values are the temperature. So first thing, calculate mean of x and mean of y. So let's see, how can we do that? We might need to get our little calculators up. let's get our calculator going. Oops, sorry about that. Let's open our TI Inspire. Here it comes. Oops, close. Okay, good. Oops, here we go. And can you remember back to kind of like your are you not yet inspired kind of activity, how you actually therefore go and calculate the mean? So of course you need to switch on, is very important. Oops, sorry, the recording was just paused by mistake. Okay, so back to here, I'll just show you what I did. So you go to on, and we're kind of wanting to do a spreadsheet, aren't we? So you might want to go across. I'm already on spreadsheet, so see spreadsheet's kind of about here. So you might want to select that. Open up a spreadsheet, and notice that ours is called time. Our X value is called time. Maybe I'll pop it over here so you can see it better. Oops, no, that's not going to help. Let's keep it back here. So we know it's time and temperature, great. There we go. Back you come. Nice. Okay. How about here? Here's good. Okay, so see, you can go up and you can give it a little heading, just so you can kind of keep track of what's going on. So here's your time. Wicked. Okay. Oh, variable not defined. Okay, that's fine. I need to put in 50. Sorry about that. Don't know what happened there. Hang on, I'll just pause. I think I did something wrong. Oh yes, I see what I did wrong. I should be putting my thing. I tried to put it in here, but I should be typing it up here. Sorry about that. So time, and now let's enter our data. So you would have entered 50 is the first time. Second time is 5. Feel free to grab out your TI Inspire and do this at the same time if you want. Oops, it's really difficult to do this on the board instead. 5, enter. Yes, it's gone now this time. 25, enter. 40, enter. 15, enter. 45, enter. Fantastic. Now check that you've entered in the right data, because as you can see, when you click on things, things don't always pop up correctly. So 50, 5, 25, 40, 15, 45. Excellent. So we've just checked that we've got the right data to start with. Okay, so we've got our data, and now we need to calculate the mean of this X value. So we're going to do, it's a data calculation. So what we need to do is we need to go to menu, because we're in a spreadsheet already. So let's go to menu. And this is topic, try to think, what topic is this? This is statistics. So we're going to select statistics, and then when you click across, sorry, let's go back to where we were. How do I get out of there? Escape. Okay, good. So back to statistics, and it's a statistics calculation. So then go across from statistics calculation. It's a one variable statistic, because it just wants us to calculate statistics just from one line of data, from one line of X data. That number of lists, correct? Yep, it's just one list, so enter. And that's all good. Our X list is, and our frequency list is 1. We don't need a frequency list. We could kind of delete that if we wanted, because it's not a frequency table. But yeah, this is our data. So our mean value, as you can see, like as you go down from here, so this was your original data. Here's telling you what the things to the right are. So to the right, that's the mean of X, so that's our value. If you happen to want to know what is the total of all these values, that's what the sum of X is. The sum of X squared, if that's of any interest to you, and the standard deviation, and so on. So there's all sorts of extra calculations that appear down here as you go further down. Standard deviation for population, standard deviations for samples, difference between the two. The total, how many variables, how many bits of data you have. You have 6 bits of data. The minimum value was 5. The median 32.5. This is called the lower quartile, 15. The upper quartile. The maximum value was 50, and so on. But the only thing from that we needed was the mean. So we know that our mean of X is 30. So that's what we've got from doing all of that. Ew. Okay, so the mean of X equals 30. Now we've got to find the mean of our values, so we get to repeat that all over again. Hooray! Different ways you can do it. You might look up a different way of doing this calculation. I'm just going to go back to here and open a new spreadsheet. So I'm on spreadsheet and open it up. This time we've got temperature. So there are ways where you can do it so you can kind of just have your X data and your Y data all on one spreadsheet. But for now, we kind of teach you that in the next lesson. So now it's temperature. So I'll pop that up in the title part, which is correct. 47, enter, 28, enter, 36, so we're just entering our data, 42. Of course, these are easy ones where you could just add all the numbers and divide by 6. So you could manually find the mean for these. So I'm just showing you what you would do if it was a tougher one. If it had like loads of data. So check you've got the right data in there. We've got 47, 28, 36, 42, 34, 41, because it's really easy to, by accident, kind of like not putting the right data. And then it's a statistical calculation, so go to menu and go to statistics. So arrow down to statistics, go to the right. It is a statistical calculation that we're doing. So go across to the right again, and it's one variable statistics. So see the top one, because it's just one list of data. So okay, that's all good. That's all good if you want. And it's come up. So see, there's our original list of data. This is telling you the mean of X, but in this case it's Y. So the mean of Y is 38. And it's telling you all the other data below too, but the only thing we need is the mean of Y. And that's the correct value. So now we can put that in our board. Mean of Y. I might just need to pause this. I'll break the board. Mean of Y equals 38. Just bear with me while I pause and recalibrate the board. Okay, thank you for your patience. I'm just recalibrating the board, and I'm going to write that properly now. Y, mean of Y equals 38 was the value we got in our calculator. Then you're asked to draw a scattergram for your data. So in your exams, you'll probably be told more specifically what to use as a scale for your X and Y axis. If not, you kind of just have to look. Okay, the lowest value in time is 5, so go down to 0. The highest value is 50, so our X-axis is going to have to go from 0 to 50. So it's one where you could easily go up by 5s, go up by 10s, that's fine. Temperature, I would suggest kind of go from 0, like the values are pretty close together though. We've got 28 up to about 47, so you could kind of like do the little staggery thing, or you could start up at 0 and go up to 50 as well. That could be pretty easy. So remember, this is your independent variable, so that has to be your x-axis, and that's your dependent variable, that has to be your y-axis. And you need to have a scale, appropriate even scale, and so on. And then you'll need to plot each point, like go across to 50 up to 47. Next one, go across to 5 up to 28, and so on. Let me show you a vague picture of one I've done below. If it will let me. Doesn't want to, does it? Okay. Try to do it manually on here. There you go. So kind of showing you, this is sort of vaguely what I did. You need to have an even scale, so it has to go up evenly. So I went up to 60 on the time. It's okay if you went up to 50, but I went up to 60. And then on the temperature, I also went 0 to 50. Plotted my points like 5 and 28, and so on. Like plotted every single coordinate, so there should be 6 coordinates in total. You must put numbers on your axes, and you must also have titles. If you don't put titles, you're losing easy peasy marks. So time and the units are minutes. Put the units, temperature, degrees Celsius. I tend to write exactly what's given to me in the table above. And then you plot your coordinates. So below is what we've done. Then you also need to plot the mean point, x, y. So this is the mean point here. So 30 brackets 38. So I'll show you below where I've done that. So here's the mean point here. I went across to 30, up to 38. Here's our mean point here. Sometimes I want you to label it capital M, but do whatever they ask you to do in the question. So in this case, they didn't ask us to label it. Then the next thing, so draw a scattergram diagram. Then you're asked to predict the temperature of a car, which has been left, plot the mean point and then draw a line of best fit, so through your mean point, sorry. So that's also what I did in blue. So here's my line of best fit. And notice it had to go through the mean point, that's really important. And then the rest is kind of using your eyes, so they might vary a bit. So you could have been slightly flatter, you could have kind of more so kind of gone through this way if you wanted to, because it's pretty close. But that's how I chose to draw it. My line of best fit, it has to go through your mean point if you didn't realize that already. Then you're asked to just use your graph to predict the temperature of a car which has been left in the sun for 35 minutes and 75 minutes. So see in purple, I've shown you in purple how I did that. Kind of use your ruler and kind of go up 35 dot 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 dot, because the dot dot dots are kind of your working out marks, and go across dot 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 dot. You might have gotten slightly lower, you might have gotten something like 41 or 42, that's okay. You put whatever yours was and put the units. Calculate 75 minutes, so 75 minutes would be way out here, so you're going to have to extend 50, 60, 70, 80. So 75, mine's a bit off, 75 would probably be here. Go up dot 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 dot, go across dot 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 dot, and in one case, you know, it's a bit hard to do because we didn't initially draw it that high. But roughly 78 degrees, you might have gotten something slightly different. And then you're asked to comment on the reliability of your predictions in D. So one of these was an interpolation and one of them was an extrapolation. Which one was which? So comment on the reliability of your predictions in D. So you can say that I was an interpolation, so reliable. So I was an interpolation, so reliable. Reliable, but I was an extrapolation. Sorry about the writing, but the pen's kind of about 20 centimeters off where the ink's appearing. And then comment on the correlation between the two variables. So correlation, let's see, would you say it's positive, negative? Let's say it's positive, and it's reasonably strong. You could say, so feel free to say reasonably strong. So I'll say a reasonably strong, but what's important is the word positive. That's probably what you're looking for. Positive correlation, which indicates that as the time in minutes increases, that causes the temperature in the car to also increase. And thank you for your patience with the board, and that's it.